You presented it there.
Presented it, there was a little bit of discussion. Questions from does it should be example boxes as well as the feedback blocks? Should it be feedback bits as well as extensions as well? The substance we can
So should we start? I think start.
Is it cold out? It's changed. It's been warm and all the rest.
It's a typical conference rooms. Either it's warm or hot.
Yeah.
It was quite cold in one of them the first day. In the big one, there were not so many people in the but mostly it's been quite warm otherwise. Yeah. So not too worries when we're expecting. Because not many people are here, but there should be a few more. Yeah.
This is fair. We've got the slack and the agenda.
Yeah, we do. We have a little bit.
When do we finish? 1:50.
So we have 30 minutes actually. I think it's 10-12 hours. And if it follows the time, then it's 2 hours. But
Yeah. We can stick to 10.
no,
But we should have.
but at least we have some leeway. But I guess, I mean, if we should start.
Let me start this going around.
Is it on? No.
I think it's not. Press the space bar twice.
Yeah. Trying to. No, there is just a push button.
It's doing something. Maybe it's on.
Is it on? No. Doesn't sound like it, right? People are not reacting.
The remote participants can hear you.
So do you hear us in the microphone?
Yes, this is Michael Romalo. I hear you fine. I see you fine. But I didn't turn on my video. I guess I could have done this too. It's my first time driving remotely, so maybe you could even see me now. But I don't know.
No, but they should hear us, right? People, yeah. Really? Okay, so do the people in the room hear us? Yes? Okay, so welcome everyone. This is the RMCAT working group. So I'm Anna Brunström, one of the co-chairs. Colin Perkins is a new co-chair joining us from this meeting. So thank you very much for that, Colin. This is the note well. I think you're all aware of it. So it, of course, applies. Oops. You just made a mess with your computer. Sorry. Today's slides are online. We have people on Metaco, so you have the link up there as well. We're going to need a minute taker and a Jabber scribe. So any volunteers? Minutes, anyone? Okay. Yeah, this one not good. Okay, so minutes. Alan, can you do it again? You did a very good job last time, so thank you very much for that. We have anyone on Jabber that wants to monitor? Thank you. Oh, okay. The next one. Okay, this is today's agenda. We will start with going over the status of the working group documents, and then we're going to have some presentations. Some of them going to be remote, so updates on the video traffic model and updates on NADA. Both of those will be remote presentations. Then we will have a couple of presentations related to the feedback and the feedback format, and then some update on the work on the NS3 module and related to the RMCAT framework from the Cisco people. Next one. Okay, so working group documents. So we've had a number of candidate algorithms getting ready for publications. So we've had the coupled congestion control out for working group last call. We got a couple of reviews, and we have also had the document updated in response. So I think the only outstanding issue that we have here is that there is a dependence between this document and the NADA and GCC documents. For NADA, this is not a problem because that document is also getting ready. It should be processed soon. For GCC, that one is a bit behind. There has not been any updates, so we're waiting for the authors to update on that one. So we will look into if we can resolve this issue to get the coupled CC out. And one possibility would be to kind of reverse the dependence and put the description of how you map to the coupled CC in the candidate drafts instead. So this is something that we have discussed between the chairs. I don't know if there are any comments on that part from the working group. There is a comment? Okay, go ahead.
Jahid, where this has been discussed? Where did you discuss this? Like,
so we have discussed it between the chairs.
Between the chairs.
As a possibility to resolve getting this document delayed for waiting for the GCC draft, which is at the moment unclear when that will be finished and proceeding.
Yeah, to be honest, I mean, I didn't even understand like what we're doing with this draft, like only focusing on two particular algorithms. Now I think we discussed a bit, and I was still not sure what we're doing on that draft, but now we're talking about again changing the draft to something else. No, so does that mean like this? The proponent has to actually go through that process?
No,
because as a Scream co-author, I don't think like we're going to do that.
Right. So I mean,
it's not. I'm just trying to make sure it's not a requirement on.
No. So this was not the intention. So from the beginning, right, what was said was that we needed to see some concrete example how the coupled CC could map to some of the candidate algorithms.
Yeah.
And that text is in the coupled CC draft at the moment with examples for GCC and NADA. And one possibility to be able to process this, I mean, we have seen the coupling, we have seen results, so we know that works, right? So this was an important part to verify that step. And now one possibility for not getting this document held up, waiting for GCC, which we are unsure when it will be finished, would be to describe the mapping in the candidate algorithms for the ones that have a mapping, not as a requirement that every candidate should do it, but it will also open up the possibility to put it for new algorithms that may come up.
Sure, but I think the current status of this draft, it is only designed or tested for NADA and GCC.
Sure.
That is the scope, and this is written in this document, right?
So
if you want to need to remove that kind of a scoping, and then I don't know like what we're doing here.
So the proposal is as I understand it, is entirely editorial.
No.
So the suggestion is that the current text, which is in the coupled congestion control draft that says how to use it with NADA, for example, gets taken out of the coupled congestion control draft and put into NADA.
But
And
I
there
don't
are
recall
two
that
paragraphs.
like a simple editorial. I think the decision was like this coupled congestion control is tested and for NADA and GCC. We had a debate. I think me and Michael talked about it for a quite long time, and then that was the settlement. Okay, Michael said, or Shafiqul's, I don't remember, but the decision was like this algorithm is only tested and for GCC and NADA.
So we can still have some informative
It's not
discussion.
informative to me, because this is not just editorial, like we just keep one paragraph out of it and put it another one. This is like whole concept. Like I was fine with that, like because I was saying like this should be in generalized. Like my question when I talked about this in this working group, I think I pretty much sure like this should work for all the algorithms, but the working group decided, or the authors decided basically, no, we'll only go for NADA and GCC.
Sure,
And now,
but nobody is suggesting otherwise.
So I think the principle is the general mechanism described in the draft, right? Then to map that to specific algorithms, you need to do some mapping and some tailoring, and that is only described for NADA and GCC.
and yeah, so that goes into one pack.
Well, so currently there is a general mechanism, and then there's a couple of paragraphs that says this is how you use it with NADA, and a couple of paragraphs that says this is how you use it with GCC. So what we're suggesting is that we keep exactly the same text, except that the couple of paragraphs that say how you use it with NADA go in the NADA draft, and the couple of paragraphs that say how you use it with GCC go in the GCC draft, and those drafts refer to the coupled draft, rather than the text being in the coupled draft and referring to the others, as a way of inverting the dependencies so we can publish the coupled draft without it having to block waiting for the GCC draft to finish, which is looking like it will take a while. And for the Scream draft, the coupled draft currently doesn't say anything about it. It still wouldn't, and we're not proposing that you make any changes to the Scream draft, but if you wanted to in the future, you would have the option to do that, and we would then not need to revise the coupled draft if you did. But if you don't, then nothing changes.
But I think Maria can fill me in here, but this is not how I recall that this algorithm was supposed to be. But anyway, I'll see. Like I'll have to read. I didn't really bother about reading it because I don't care about it. So I have to read the draft and see like how it is written. But it is not editorial, only editorial as I see it.
I mean, it is, because all we are proposing is you literally take the two paragraphs that are already in that draft and move them into another draft. We're not proposing any changes to those paragraphs. And we're not proposing any changes to the scope of the coupled draft. So.
Yeah, could I just have a question as an individual contributor? So that means would the coupled congestion control draft not have any, not have like one single mapping in it? So basically it would just be like the raw skeleton without knowing how to apply it to a certain congestion control?
Right.
Yeah. Like Michael, or did you also tried it with other non-RMCAT standardized congestion controls, right?
Michael Wells, we tried it with a ton of congestion controls that have nothing to do with RMCAT. We tried it with NADA and GCC, which was a decision that was made here. These are the two that are described. These are the two it works with for RMCAT. The text is in there. It now says it's for these two. This is an editorial change that's proposed that we authors agree with, where this text goes out and is moved elsewhere, such that the normative reference doesn't hold up that thing from publishing. And you can have an informational reference about whatever you want, but I mean, that's what it is. It's a text change.
I'm wondering how useful the document is if you just have it as a standalone document without
It is
having
not a
that
standalone document because it's a normative reference. It is not a standalone document because it's a normative reference. It points at this normative other one thing that is going to be published before that is published because it's normative.
But then you don't resolve any problem, any dependency.
So I mean, the
No. Okay. I see. Yes, because NADA can be published with this.
I mean, the
That's not the
proposal
problem.
is
It's that we wait forever until GCC gets published.
Yeah.
Possibly.
So, I mean,
right?
the proposal is literally that we take these two paragraphs and move them to the GCC draft, and these two and move them to the NADA draft. So, Colin, I'm reading from the draft. It says in the abstract, it specifies how to apply the method to both NADA and Google condition control. That's on the abstract. So basically, this whole specific memo, the whole document, is for NADA and GCC. So it cannot be generalized. It cannot be standalone.
So it's not, yeah, the mechanism described is general, right? And at the moment it has the mapping for the two. I mean, it's also a possibility to split it. But what we are trying to do is to find some way to not get blocked so that we can start to get some documents published.
This one, how do you read this one?
Hi,
But
this is
then
Xiaoqing.
actually, I mean, it went through the working group last fall, right? So shall we call it again then, working group last fall again? Because that's like pretty fundamental change to the document. I mean, I'm fine with the change in the text if you want to do that, but then you have to go through the working group last call again, right? Yeah. Or?
Hello, this is Xiaoqing. I've been in the virtual queue. Is there any other way I can speak?
Yes, please, Xiaoqing.
Yeah, so I just wanted to provide my input mostly as the author for the NADA draft, but also maybe more as a suggestion to a tweak of the arrangement. So I understand that the proposal is to just make editorial changes, but I also understand the concern that without showing any concrete example in the coupled congestion, sort of in the coupled CC draft, that was one of the main critiques, if I remember, from the earlier round of reviews of the draft. Maybe one compromise could be that since the NADA draft is getting close to working group last call, right? Presumably around the same time frame, maybe we can keep the description of basically how coupled CC applies to NADA draft still in the coupled CC draft, assuming that, the NADA draft will not be blocking it very soon. Whereas for GCC and any other incoming, sort of potentially new algorithms, we can request new candidate algorithms if they wish, to also describe how this works with coupled CC. And as I understand, it's not a prerequisite, right? So for instance, Scream does not need to mention it because it's not in consideration. The GCC, since the results are already there, it's more about giving them the text to embed. Maybe that's a way to show people not only how the original design has been sort of tested out in a concrete manner to one of the given solutions, but also show people a way on how to, as new algorithms come in, an example of how to accommodate coupled congestion control. That's just mainly my suggestion. Yeah.
Michael Wetzel, I'm standing here waiting for my turn because I wanted to propose exactly the same. But as an additional suggestion, maybe we can keep the GCC text in an appendix as informational, with an informational reference pointing at the paper and saying this is one possible implementation for the version described here, something like that. But keep only NADA as a normative.
Sure. Yep.
But I agree with this change completely. That was my what I want to suggest.
Yeah, so I mean, NADA is not a problem, right? Because that is progressing, and we're going to see that we have a clear plan for that. So what we're trying to achieve is to avoid getting blocked on the GCC draft, as we are not clear when that will be finished and published. So I think that's a good suggestion.
I mean, you know, if this is too controversial, we'll just leave the text as it is, and all it will mean is that the coupled draft sits in the RFC editor queue until GCC is ready. But that seems like a waste, but that's the only impact it would have.
So let's see if we now go with the proposal that Charjing and Michael just proposed. Is that acceptable to everyone? Too far from it.
Right. So
So what is the suggestion on because you said something and Colin said something. So what is the proposal, concrete proposal to us?
So the concrete proposal was that we were originally making was that the text on NADA moves to the NADA draft and the text on GCC moves to the GCC draft. And this says this is a couple congestion control mechanism that could potentially be used with other candidates, and see the candidate drafts, and those that care will have a description of how to do that. The Scream draft, by the sounds of it, would not have that description, and that's fine. Now, as I understand it, Charjing suggested that maybe this could keep the text on NADA in it, and the stuff on GCC could move to the GCC draft. Or if this really is so controversial, we'll just leave the text in the place where it is, and the only impact of that will be that the coupled draft gets into the RFC editor queue and sits there waiting on a normative reference on the Google congestion control.
Yeah,
which is not the end of the world. It's just a bit annoying because it sits there, and I don't know how long the GCC is going to take.
I don't know. I cannot. But it seems like I don't know like what exactly problem we're solving. We're solving like this endless staying of this draft, or
Okay. We're just trying to get this draft published quicker.
Yeah. Okay. But I mean, we should do whatever to actually do that. But as I pointed out, the whole time this draft has been discussed on this particular specification, like examples, and the authors have selected 2 of them. And then when I reviewed as a SLA solution that was tested and specifies how it should work only for 2 algorithms. And that's how I perceived it. That's how he went through. And now all of a sudden, changing that doesn't really make sense to me. But we should try to solve the problem. I mean,
okay,
what
so
we're trying to do. But Charjing's proposal looks okay with me, because all we need perhaps a single kind of example, right?
okay, so we've had some proposals for how to resolve it. So would it be acceptable if we leave the NADA description in the coupled CC and we can put some information for GCC, or we have more comments?
Harald Alvestrand, +1 to Michael and the lady whose name I didn't catch. If GCC is delayed, make that reference informational. Sitting in the RFC editor's queue is not a disaster. I'm sitting there with about too many, but let's just do it.
Yeah, so I think you shouldn't really base decisions on sitting in the editor queue. Like at that point when it's in the editor queue, it's out of the working group, which is the more important part, because you can say you're done with it, and sitting there, it doesn't really matter that much.
I don't see it.
Yeah. Okay. So it seems we don't have consensus on this. We will try and formulate a proposal to take to the list. And if there are still objections, we'll just leave it as it is. And if the worst cases will be that the coupled draft just sits in the RFC editor queue for a while.
Michael Welzer, maybe I misunderstood. We don't have consensus on the case of, so if we suggest to move to cite GCC as informational, don't we have consensus on that? I thought we have.
The way I heard it was that Zahed was still objecting to that, but if that's not the case, then...
Yeah, can we ask him? Zahed? GCC informational, otherwise changing nothing, that's the suggestion.
Well, what you do with GCC, I don't know. But if NADA authors are saying like it's fine with it only specifies. I mean, all I am asking is like an example, and NADA says like it's fine with them. So go with NADA, and then what do you do with GCC? I mean, informational or not, I mean, in the appendix, I mean, why does it matter? So I'm fine with what Xiaoxing said, but it's up to the author, like what they want to the GCC.
Okay, good.
So Harald Alvestram was also giving a +1 to that. So it seems to me that we have consensus on turning the reference to GCC informational and going ahead like this.
Okay, so what I suggest then is that you, as the author of the coupled draft, come up with a proposal for exactly what changes that would entail.
Only a reference.
Yeah. I mean, that would presumably say take these 2 paragraphs out and move them to wherever.
Okay, can do. Yeah, okay.
Yeah. And
put to the appendix and make it. Yeah, okay. Change the text a little bit.
Yeah. Yes. Right. Yeah. So the suggestion is Michael comes up with a proposal for how to do that, whether that is moving the GCC paragraphs to an appendix and making it informational, or whether it's moving them to the GCC draft and referencing it as talk to the GCC people and figure out what's the right way of doing that, and come up with a proposal, and we'll take it to the list.
Okay.
Harald Alvestram, adding it to GCC will be more controversial than having normative reference from this to GCC.
Michael Reitzel again. So I think we have a concrete proposal on the table.
Okay.
And consensus on it, I think.
So please send suggested text changes to the list, and then we'll confirm on the list.
Okay, so this was the coupled CC draft. Then we have the shared bottleneck detection draft. This draft is in working group last call. It's ready, so please help review it. So it's going for about 2 more weeks. And then it's, depending on the feedback, I think we are ready to move this draft forward. Next slide. Then we have Scream draft. This draft has also passed working group last call. It has been updated in response to that. So this one is also ready to move forward. There's also been an IPR disclosure on it, so just making sure the group is aware of that as we proceed. The NADA draft has been updated, some smaller algorithm modifications, and adding the information about what experiments are needed to take it forward. So we will have a presentation on that on the agenda. And then we think this draft will also be ready for working group last call. So that is in the pipeline after the SPD draft. And there were also some IPR issues raised on that draft as well. So that's just making you aware of that. The GCC draft, this one is waiting for the authors to come back with updates. So there we are waiting on that. The requirements and the interfaces evaluation. So we have the requirements draft still in the editor queue. Then we have the eval criteria and the eval test draft. So the eval test has been updated so that they are now conformant in relation to the TCP model. There was also a discussion in the last meeting about separating the 2 background test cases. This, I think, is not in the draft yet. Right? I'm looking at one of the authors now. So there are still some smaller updates, I guess, on these drafts, but they should be ready soon as well. So when we get to the discussion on the time plan, we hope to move forward with these drafts once we get the candidates finished and sent out. The wireless tests has also had some smaller updates, and we will have a presentation that relates to that later today as well. Sorry, we will not have a presentation on that. We will have a presentation on the video traffic models that is coming up later. And then we have the CC codec interaction draft, which is expired, but this is kind of waiting on the framework document draft, which is currently an individual draft. We have the work on the feedback. So we have Colin's draft looking at the amount of feedback that you can send, and there's a presentation on that on the agenda, as well as, yes, next slide. as well as the design team feedback draft, which is an individual draft at the moment. And we then also have the framework draft that will be discussed at a later point. So this we had up at the last meeting. There was some feedback there, and there's been some more discussion on what needs to be incorporated. So there will also be an update from the authors after that. And then we have another individual draft that Arun presented last time, which is also an individual draft, and which is expired, and we will see what the authors will do with that. So the milestones, we are behind in our milestones, so we are going to update all of them. We have a suggested time plan on the next slide. So what we will try and do is to get the candidate algorithm drafts out of the working group, hopefully by the end of this year. Maybe with the last ones, it will run into January because we need to have the working group last calls, but we think that they will all be shipped soon. Then our suggestion is that we will try to focus on getting the evaluation and interface drafts out, and also finishing up the design team work on the feedback. And maybe this could be finished by the Chicago IETF, not all the drafts, but some of them, some of the evaluation drafts ready and finished, and maybe the agreement on the feedback, so that we can also finish up that work item. And then we will have to discuss how to proceed in terms of what evaluations will be needed, and how will we track the progress of the experimental candidates that we are now sending out, so that we can then also look into how we will move the work forwards towards standardizing one or several of those algorithms. So that is a suggestion discussion we suggest we take up at the next IETF meeting, trying to get these drafts submitted first. So we have a fairly small amount of people that work on most of these drafts, so we think we need to have them a bit sequential here. It's not that we get a lot of voluntary reviews on the drafts when they have been out, so we are probing a bit for those. So please help review in the process here. So any comments on this proposed timeline? Does this seem reasonable from the working group's perspective, or? So I think we have a number of work items that needs the last effort to get them out of the group, and it would be really good if we could finish that up, so we can then think about the next steps after that. Okay. If there are no comments on that, then let's move on.
Next is judging.
So it's Sergio or Xiaojing, or both of you. I don't know who will want to start, but.
Hello,
yes,
Sergio
so
speaking.
Sergio will present. Yeah.
Sorry. Yeah, I'll present the first half, and then Xiaojing will present the second one.
Go ahead.
Okay, so
we have the slides up. Hopefully you can see them.
Good. So thank you. Good morning, everyone. So my name is Sergio Mena, and together with Xiaojing, we're going to present the updates on the video traffic model draft, which in the last months has been focusing on using the Mozilla web browser. Next slide, please. So we have used the Mozilla browser basically for analyzing the transient behavior of the codecs it ships with. And this is the outline of the talk. So I'll first explain why we did this, then how we modified Mozilla browser to fit our goals, then the advantages of doing this, and then Xiaojing will present a set of plots showing our results and what we are planning to do next. Next slide, please. So why we did this. So back in Buenos Aires, Xiaojing presented an extensive set of results on our analysis of the transient behavior of the X264 codec. We were using X264 with non-standard settings. For instance, we were using an initial iframe, and everything else was p-frames, however big they may be. And the video sequences we were using was what was available at that time, which were basically animation sequences. Those are the only ones we had which were long enough. These had scene cuts that could be seen in the traces. So the group, the ARMCAT group, gave us 2 feedback items to consider. First of all, that the animation as video sequence is not really representative of video conferencing. And most importantly, that X264 might not be the best choice of a codec for live encoding. Not many people use it out there for that. It's mainly used for offline encoding and decoding. So in the last months, we have addressed these 2 items. So we have produced a conferencing-like video sequence that I'm going to describe in a minute. And Randall Jessup has volunteered to help us with the Mozilla browser. I would like to take the opportunity now to express our gratitude to Randall for his help and support. Next slide, please. So how we did it. First of all, I'm going to focus on the video sequence. So we have tried several things, and in the end, the one that gave the best results was using a Cisco telepresence unit that Xiaoqing configured to capture a file locally of the right length, 6 minutes, more than enough, the right resolution, the right frame rate, and having 3 people, moving their hands, nodding their heads. So conference-like content, basically. And we could not configure with 0 compression, but the compression that we had was very light. The bitrate that of the resulting file was 4 megabits per second. We believe this is not impacting the results that Xiaoqing is going to present later, especially in the case of 720p, because the original is 1080 and we have results for 720. So basically, we converted that into a format that could be read by our modified Mozilla browser, which is in next slide. So what we did with Mozilla was a set of limited changes to the browser. The first change set was basically to disconnect the output of the congestion controller from to the input of the codec. So basically, rather than the codec obeying what the bandwidth estimation that the congestion controller was giving it, it was just following a fixed pattern of bit rates that we had coded. This is actually what was done by Randall. And the second part was to read frames from a file rather than live capturing from the webcam. Next slide, please. So once we had the right video sequence and the modified browser, we were all set to gather our traces and do our study. And for that, we used an HTML file that is using WebRTC. It's a slightly modified version of one that folks at Mozilla use for testing, and it's basically a one-way conference, so one sender, one receiver, and both are sitting on the same host. We run the experiments basically on my laptop. I'm putting here the details, the specs for reference. And while running the tests, I was monitoring to make sure that the CPU, the memory, and the hard disk were not overloaded by the test itself. Next slide, please. And so this is the way we gathered the results that Xiaoqing is going to present right away. And the advantages of this is basically that we address valid concerns from the group. First of all, we now have teleconference-like contents of with the right characteristics, right length, right frame rate, right resolution. And we used, rather than X264, we used a widely used browser that many people use for teleconferencing, and we were very careful enough to keep the default settings, and we were using the codec that shipped with the browser, which means that the usage that we were giving to the codecs were basically representative of an average user that using Mozilla browsers, or Firefox, would be giving to these codecs on an average video conferencing session. And finally, the fact that we are reading the video sequence from a file rather than the camera gives us full control on what we are encoding. Of course, the tests are easy to run. You don't need to wave at the camera, etc. And the results are repeatable. For instance, if you repeat the test for 2 different resolutions, which is what we are going to present later, and you focus on a particular frame, you know that for that frame in both tests, the actual raw frame, original frame, was exactly the same. Next slide. So I now pass the ball to Xiaoqing for presenting the results.
Yeah, thank you. Next slide, please. Yeah, so going forward, I'm going to show you guys some of the sample traces we have collected. We've mainly collected two collection of sample traces by following a time-varying target rate changing pattern. As Sergio has mentioned before, that rate changing pattern has been hardwired so that it's more repeatable. And it's basically, the idea is that we're using the target rate of 1 megabit per second as the reference rate. And once every 20 seconds, we will choose a target rate that's either above or below that reference rate, and then come back to it. And we choose target rates that are 20, 40, and 60% above or below the reference rate of 1 megabit per second. So that's why I hope you guys in the room can see a better resolution rendering of this graph. Basically, here we're plotting out the raw frames encoded frame sizes. This is for the embedded open H.264 codec, the raw embedded frame sizes over time, as well as a time smoothed version, which is time averaged over the recent 6 frames, and with a frame rate of 30 frames per second, that corresponding to a local averaging over 200 milliseconds. And finally, you should be able to see the black dashed lines, which correspond to the reference target rate. Sort of the reference frame size corresponding to the target rate that the ideal, CBR traffic would have generated. So a couple of things to note here. One is that because we're changing our rate kind of abruptly once every 20 seconds, we do see that it triggers a big frame, and we don't really know the frame size, but we suspect these are sort of key frames or iframes that are reacting to these changes, also on the order of once every 20 seconds. And secondly, obviously, we don't see constant frame sizes. We see frame sizes that are fluctuating quite a bit around the target that the codec is trying to to converge at. So this is an overview graph just to show the temporal pattern of the target rate that we've chosen. If we advance to the next slide, we can basically see a zoomed in view for one of the transitions that we're interested in. For instance, upgrading from a target rate of 1 megabit per second up to 1.6 megabit per second. So again, the top graph is with the lower resolution of 720p, and the bottom graph is for 1080p. But we do see, as Sergio has mentioned before, fairly close correspondence of the behaviors for these frames. So the thing to note here is that for once, like for the 720p frames, we do see that the encoded frame sizes tend to be vary a bit more around the target rate. And for the 1080p, for some reason, the codec is doing a better job at sort of converging on the target rate. And the second thing to notice is that at the transition period, it does generate a big iframe, and then that's followed by a few smaller frames than the target, really to keep within the rate budget, right? The live video encoder is trying to abide by over time. So these are the things that at least qualitatively correspond to the behavior we have described in the video traffic model draft. And one thing we'll go back to do is to sort of also quantitatively measure the overshoot ratio as well as the duration of the transition, etc., to drive the parameters that we have proposed, basically to revise the parameters that we have proposed in the video traffic model draft, now that we have collected data from a representative codec in a widely used browser. So this is showing the behavior of the codec output for an upshift. And in the next slide, we're showing the other side of the story, basically when the target rate downshifts from 1 megabit per second down to 400 kilobits per second. So we see similar things, except that now at a lower target, lower target rate, the output frames seem to be sort of fluctuating tighter around the target frame size. Next one. So these are for Open H.264 codec. So the next one, the corresponding set of experiments are using, basically switching to another codec, the VP8, and following exactly the same pattern, using the same video sequence, so that the results are actually quite comparable. So basically we can compare results against the previous set of results using Open H.264. One thing at least I personally have observed is that using this VP8 codec in the outputs, the big frames are not as regular as in the H.264. And the other thing is that it might be a bit harder to see, but it depends on the resolution of this figure, that sometimes the VP8 codec fails to achieve the target rate at 1 meg per second. We do have a zooming graph for that. So if we switch to the next one, so this is the case where we caught basically for the duration between 40 and 60 seconds, whereas our target rate was at 1 megabit per second, the VP8 output sort of significantly stays below that all the time. I've previously shared this set of results with Randall already, so he was pointing out that potentially there could be just, maybe misconfiguration of API or bugs. So let's take that, sort of, let's not read too much of it, but that is one of the things that we have observed from this set of experiments. And other than that, the target, basically the generated frame sizes fluctuate quite tightly around the reference frame size. And the next one, the next graph basically shows how the codec behaves, again, from jumping from 1 megabit per second to 1.6 megabit per second. If we mentally record the graph that we have seen using the Open H.264 codec, one major difference is that it seems that it took the VP8 codec a bit longer to sort of climb back from that, the succession of smaller frames and then convert. Basically, the convergence time is a bit slower in VP8 compared to Open H.264. And the next one. This is the corresponding part where we're jumping down in rate from 1 megabit per second down to 400K. So here again, the slope of change for a VP8 is took a bit longer. And other than that, so again, the amount of fluctuation of the frame sizes around their target frame size, that's one thing that we will basically later on we'll perform some analysis to extract out the fluctuation ratio for steady state analysis of basically for measuring the statistical behavior of these codec outputs. But qualitatively, again, these do match quite well with the behavior that our video traffic model is trying to follow. Next one. So far I've shown all the traces for the video frame sizes and their fluctuation around the reference. We have observed similar behavior for the frame intervals, simply because these are, sort of output from a live encoder. We don't really get a steady, fast, constant frame interval at their target of 30 frames per second. We have observed some fluctuations in the frame, basically from frame to frame in the individual frame intervals. So instead of bothering you, boring you guys with even more graphs, we're just summarizing that information using sort of the histogram for the four collection of traces that we've got. Obviously, they all peak around the target of 30 frames per second, which is the reference frame interval of 33 milliseconds, but we do see deviations on both sides of the distribution. Next one. So with that, obviously, and also from our traces, I've only shown sort of two set of examples for the rate upshift and downshift, but the trace itself contains information about how the codec behaves for other step sizes of the upshift and downshift. So there's more, and as I mentioned before, we'll go back for the analysis, and hopefully the example, but qualitatively they follow very similar behaviors. So it's more a change, basically a difference in degree. And in terms of the observations, as I mentioned earlier, we have observed fluctuation of the frame and interval, and we have noticed that the VP8 encoder occasionally cannot meet the target output rate. That's something pending further investigation, I suppose. And also, we have observed the presence of big transition frames, both for the rate upshifting and downshifting part. And this part is quite different from our previous set of observations using the X264 codec. But now, since we have much more confidence, right, in the codecs that are being used embedded in the browser, we're going to go back to our draft and revise our description to really follow more closely what we have observed from these traces. And finally, as I have mentioned before, if we were to compare the Open H264 and the VP8 codec output, during transition, it seems that VP8 takes a little bit basically VP8 takes slightly longer to converge. Whereas for H264, it seems to be needing only a few frames to jump back to the target reference frame size. So next slide, please. So with that, we've only completed kind of the first step of data collection. And with that, we'll continue with our analysis of the data and correspondingly update the drafts. So the drafts the part in the draft that will need to reflect our observation would be both in section 5, where we'll provide concrete values to the statistical models that describes the transient behavior of the draft, and also in section 7, where we describe there is a threshold for basically introducing the big transitional frames. So we basically want to make sure that our draft now reflects more sort of faithfully what the data tells us. And also, as some of the people who have been following this draft already knows, we have also open sourced a collection of, basically we have also open sourced a code repo called SynCodex, which is a reference implementation of these video traffic models. So obviously now with the new data, we will be able to feed the frame size information as a new set of traces for the trace-driven model, and also we'll be able to adapt change the parameters in the statistics-based codec with our results, and also update the steady state traces using these data. And also we have this idea of proposing a hybrid model which follows the trace-driven model during the steady state, just because those frame sizes are collected from real-world codec outputs and naturally reflects the fluctuations in the codec outputs. But then during the transient, since it's very hard to collect data for all combinations of rate transitions, we can follow the statistical model, but feed the model with the realistic parameters based on our analysis from the data. So that's how the collection of experimental results this collection of experimental data will influence how we go forward in terms of revising both the draft and our code implementation reflecting the draft. That's the end of our presentation, I believe. Actually, if the chair could flip to the next slide. Oh, actually, the one after that. This is just a quick a screenshot of the video that we have captured, just to give people a flavor of the type of video content, as Sergio was mentioning, we're trying to mimic like an interview or, chat type of scene, which is quite typical in one of our conference rooms in the Cisco's office. Yeah. And we have a few backup slides on the traces, but it's more for, in case people have questions, we can have something concrete to show. Yeah, these are for the frame intervals. Yeah. Thank you.
Okay, thank you, Xiaoxing and Sergio. Do we have any questions or comments? Okay, if not, then we move on to the next presentation, and that will be on NADA.
Okay, yeah.
So that's again Xiaoxing, so floor is
Sure.
yours.
Okay, thank you. Yeah, so I'll give a fairly light, status update on the NADA draft. Yeah, next page, please. Next page, please. Yeah. So basically, there are two parts. We have actually updated the draft after the Berlin meeting, and so we updated the draft somewhere in September. And the draft contains a bunch of fairly minor algorithm updates and also some editorial changes suggested by the chairs. So I'll go over those quickly. And then since we have tweaked the algorithm a little bit more, I'm just going to show one set of example evaluation results. Unfortunately, can you guys still hear me correctly? For some reason, yeah, I'm seeing some kind of a...
Yes,
okay,
we can still hear you, but your picture's
Sure.
disappeared from the screen, but that's fine.
Oh, okay, yeah. Now, yeah, basically, I'll just, for the algorithm update, since it only affects the scenario where NADA competes against TCP, I'll just show one set of evaluation results to validate that portion, as opposed to, repeating the entire suite of test case. We do intend to do it, but, maybe after, when time permits later, and then describe briefly our next steps. Next page, please. So now the draft have been updated from version 02 to 03. The main change was in the algorithm tweak, where we basically made some changes to the equation that we use for reflecting the nonlinear warping part of the congestion signal calculation. I'll have one extra slide to describe that more concretely. And also, since people have been implementing this draft and trying this out, I have received some feedback in, sometimes it's the original version of the draft were not very clear in describing when to invoke this nonlinear warping. So in this new version, we have specified the rule in a more concrete manner. And then finally, in terms of the content changes, in this new version of the draft, we have added a section to suggest additional additional suggested experiments. Those are the things. Some are still in our own queue for trying out, and some we just think we encourage people to try them out. And finally, it is basically there were some typos and calculation errors in embarrassing calculation errors in the previous versions of the draft, and we took the opportunity to correct them. Yeah. Next page, please. So the main part of the algorithm, it was actually a swapping the equation. So actually, let me describe the criteria for invoking the nonlinear warping part first. So now we have specifically described in the draft to say, basically, we will invoke nonlinear warping of our congestion signal, basically to perform a one-to-one mapping between the measured queuing delay to the congestion signal. But we'll perform that warping only there has been losses observed recently, and we have proposed a concrete rule to define what it means to be recently. Basically, it's whether losses have been observed in the previous time window of a parameter. And we have also described the default value of this previous time window parameter in the draft. And that was based on our observation of the potentially TCP sawtooth behavior, the typical, let's say, width of the sawtooth. So that is for clearing up our criteria for invoking the nonlinear warping part. And now for the warping itself, we have proposed a slightly simpler form of the equation as shown here. Basically, the fall-off part when the queuing delay increases, and when the queuing delay exceeds the threshold and increases, our congestion signal will be designed to fall off, and now it falls off following a negative exponential form, just so that the mathematical formula is simpler to take, and also the parameters that's embedded in this is sort of easier to understand. The threshold simply dictates the reflection point of when to apply the nonlinear warping, kind of when congestion signal starts to decrease as opposed to increase with observed queuing delay. And secondly, this new parameter lambda is some degree of freedom will allow us to tweak the how aggressively NADA can compete against other loss-based flows. So in the next slide,
there's a question from Jabber.
Sure.
From Ingemar Johansson. Does this mean that the warping is disabled when no packet loss detected?
It is correct that no packet loss has been detected in the throughout the previous time window. So, for instance, if basically your last observed loss, if it falls out of that time window, then we will no longer apply the warping. Yeah. So this is an illustration. Okay. Yeah, so this is an illustration of the nonlinear warping function. The original form we used was in the blue is shown in blue curve. Basically, the part where it falls off follows a fractional polynomial form, whereas in this new form we're using a inverse exponential form, and because we can tweak the parameter lambda, kind of the shape of this exponential form to allow it either to fall off more gently or fall off more drastically, that would drive the NADA competition against losses either more aggressively or if we have more residual warped delay, then NADA will be yielding more shared bandwidth to competing loss-based flows. So we're giving ourselves a little bit more degree of freedom to tweak its aggressiveness. And the blue and the black curves correspond to two different values of the lambda. And currently in our implementation, we recommend the red version, which is more basically, as the results will be showing, is it's a bit more TCP friendly. Next page, please. Oh, by the way, this lambda thing is fairly recent. We haven't updated the draft with it. I'll do a quick maybe round of update on the draft to reflect this introduction of the new parameter. Now, the two set of results we're showing is basically for one NADA flow competing against a long-living TCP flow. The TCP flow shows up in the middle of this experiment from time 60 seconds to 240 seconds. So, and we're only plotting out the streaming rate of the NADA flow. So obviously in the middle, when it dips down, that's the duration when TCP flow is active. And correspondingly, we're seeing the increase in the queuing delay and also the measured packet loss ratio by the NADA flow. So this is using the lambda value of 0.5, where it falls off more gently. And in the next page, it's the same experiment, except that we're using a lambda of 1.0. If you recall from the previous graph, that corresponds to basically the nonlinear warping function falling off fairly drastically. So in this specific example, the NADA flow basically almost manages to stream at its maximum rate, and leaving more like the residual of 500 kilobits per second for TCP. So it's more aggressive compared to the previous version of it. So we think, sort of leaving a knob for tuning the aggressiveness of this delay-based algorithm when it competes against loss-based flow is a good idea. It, gives you a little bit more freedom of choice. Next, but admittedly, we have only carried out limited evaluations for this new flavor. One thing we do know is that it does not really affect cases where the NADA flow competes against itself, or sort of in the delay-based mode only, since it only impacts the shape of the nonlinear function. But for our due diligence, we do plan to sweep through all the evaluation results again. Yeah. Next one. So that's the main update we have for the NADA draft. For our next steps, we're basically working on implementation of this in a new, kind of a fresh implementation in standalone modular for the NS3. We have a separate presentation towards the end of today's meeting to describe that a little bit more. But the idea is that previously we have two different versions of implementation, one in NS2, which increasingly becoming more obsolete as people are moving to an NS3. And previously we do have an implementation of NS3, but that older version of the code was slightly tied to our internal product code, so there were certain API restrictions. Since we've been working on coming up with a standalone, modular in NS3 for reflecting the entire RMCAT congestion control solution framework, we basically re-implemented the NADA congestion controller as a pluggable controller to that framework. And that also gave us a chance to follow the draft descriptions more literally, and hopefully it can be a easier to follow reference implementation once we are able to open source that code. So that's more on the implementation side. And obviously now, since we have a fresh implementation of it, we're also updating all the evaluation results in NS3, which we already have all the test suits. We're basically redoing all the work, but just to make sure things still follow through as expected. And finally, we have suggested a collection of additional experiments in the draft, and we're trying to make progress on those our own, at our own steps too, because we do think these are valuable tests to try out, especially for things like the presence of AQM schemes, the influence of ECN, and also how the algorithm performs when it is being driven by a synthetic video traffic source instead of the perfect CBR-like traffic. And with that, we do think that the draft, the algorithm has converged. If you allow us more time, we'll probably come up with more tweaks. So it may make more sense for it to basically to go through a working group last call, and to to basically to converge as opposed to keep tweaking it all the time. Yeah.
Okay, thank you, Xiaojing. Do we have any questions or comments? So you are gonna update the draft?
I'll update the
with
part on the
lambda?
new parameter that we introduced. Yeah.
Yeah, with the new factor,
shortly
and
after the meeting.
also validate the results on the test cases with this version, I
Yeah,
guess.
and the entire collection of test cases. Yeah. I'll probably send out like a slide deck on the email. To the mailing list.
Okay, perfect.
Yeah.
Thank you. Okay, then we move on. The next is Sahid with the report from the feedback design team on the status.
Hi. Thank you, Hannah. I'm going to very briefly tell you what we have been doing in the RMCAT design team that is formed to actually work on a RTCP condition control feedback message, condition control message. So next slide, please. So since IETF 96, we have met 2 times with lots of participants, active design team members, and there has been some small gatherings while we were writing the drafts and stuff. So the 00 version of this DT RTCP feedback RMCAT RTCP feedback message has some fixed means, mostly talking about if you want to do this report timestamp, what would be your clock? Then there are a couple of format specific fixed means that we decided, okay, unless we have a kind of frozen the packet format, there is not really benefit to work on it. Then there was some discussion in the mailing list, and also we took the discussion to the design team about these low bitrate use cases. So we're talking about very low audio, like 20 kilobit per second. I think Stefan Holmar has presented some of them in the mailing list. I think Randall was also posting them. So we took that discussion, and actually with the help of Colin's draft, we kind of analyze and see like, well, how much RTCP bandwidth we can get. I think Colin will cover that one later on. So we discussed that one. Then there was some, I think there was one mistake in our 00 version. There was SSRC that has been updated in 01, and also we added a section in 00 version. We had this XR block, and with 01 version we have a XR block and feedback messages, RTCP feedback messages separate. It's just same information at 2 different kind of packet, one addressing the both APP, APPF, kind of when you send it in a regular, and when you want to send it in an APPF, you can use this feedback message format. So yeah, I think the current packet format we have also, I think Colin has helped us, and I think Randall and Stefan also worked on the analysis. We have an analysis of how much with the current format, current packet format, how low you can go on the RTCP bandwidth. Then we also looked about a little bit optimization, kind of like a separate kind of alternative approaches. Like now in this current format, we have loss bit and ECN marking bit and arrival time offset information. So we are thinking about what if we have how much you can compress if we take out this ECN and loss bit and have a run length encoding kind of idea. And the idea was well, the ECN kind of like depends on whether you have a path that supports ECN or not. So maybe ECN will not be available in all the sessions that the communication will be running. So maybe it's a good idea to actually separate it out from the power packet information. So basically, we have 2 proposals right now that due to lack of time, we didn't go into detailed analysis, so it was not part of this 01 version. The idea was to I think we have a slot there. Michael is going to talk. I don't know about Varun if he has slot and going to talk about it. But the idea is we take the discussion now as we haven't analyzed the new proposals, and if it looks okay, then we just merge it, and we have a 02 version of this packet format. And our target is we should be able to get completed something concrete by next IETF meeting. That means this design team at least will run up to next IETF meeting, and we perhaps in between these 2 IETF meeting will be meeting more frequently so that we can have a substantial progress and we can show you the final outcome at IETF 98. So that is brief update. I think we'll learn, we'll get more information. I mean, Colin going to present this RTCP bandwidth calculation. Then Michael is going to present the new kind of when you take this ECN out of it and compress a bit these packet formats later these presentations.
Okay, thank you, Said.
Thank you.
Then you're up next, Colin.
Okay, this is Colin Perkins speaking from the floor mic as an individual. This draft is the design team feedback message draft. The authors listed on this slide are myself, Zahed, Varun, and Michael. Those are the people listed as authors on the draft. It's reporting on work which was discussed in the design team, which has a number of additional people involved in that as well. This is not my draft. I'm not representing the design team. Zahed asked me to give an update on the changes which are in the 01 draft. So what I'm going to try and do here is outline what's changed in that draft, and I also have some comments which are my opinion on the overheads of that, then I think there's a presentation next to Michael for some proposed changes to this draft, and then after that I will be presenting some discussion of the RTCP overheads with this draft. Okay. Next slide. Okay, so the goals of the design team were to build a common congestion control feedback format. It's supposed to be a RTCP packet format that allows to convey per packet arrival times, per packet feedback on whether the packets were lost or received, and per packet ECN feedback. The brief for this was to send feedback in both scheduled compound RTCP packets that can go into regular reports, and as AVPF early transport layer feedback for more immediate feedback. And we're trying to define both packet formats at this stage. Next slide. Okay, so to start with, I want to discuss the feedback in the scheduled packets, and then I'll go on to the non-compound early feedback packets. So with regular scheduled RTCP, the endpoints send the packets according to the bandwidth calculation in RFC 3550. The frequency of the reports depends on the allocated RTCP bandwidth, and that defaults to being 5% of the session bandwidth. It's configurable in SDP up to whatever value you like. 3550 by default has a 5-second minimum RTCP reporting interval, but also allows reduced minimum intervals, which can get considerably smaller. And if you use the AVPF extensions without the rapid feedback, you can also just reduce the interval even smaller. Regular 3550, the reports must be a compound RTCP packets. They need to start with either a sender report or a receiver report. They need to contain a source description packet with at least a CNAME item and optionally other source description items. And they can then have other RTCP packets following it. The RTCP XR extensions provide for detailed reception quality feedback. So what we've done here is define an XR block for congestion control feedback that can be stacked in a compound packet, along with a source description packet and a sender report or a receiver report. Next slide. So this is the format we're proposing. What you see in the diagram at the top, labeled with the red XR header, is the standard RTCP header with the XR block type and the SSRC of the packet sender. Following that, labeled green congestion control report header, we have the XR block header with the block type specifying the congestion control feedback, the report count, the block length, and a timestamp of the report. And then for each source which is being reported on, we have an additional congestion control block which has the SSRC of that source, the beginning and ending sequence numbers of the range of packets which are being reported on. And then for each packet, we have a 16-bit field containing a single bit to indicate whether that packet was lost or received, 2 bits of ECN information being echoed back, and an arrival time offset relative to the report timestamp. and the precise format of that arrival time offset and the report timestamp are to be determined. There's not an obvious clock rate to pick. It doesn't necessarily make sense to have them as using the clock rate of the sender of the XR packet, so we'll have to figure out what an appropriate clock rate is and what an appropriate format for the arrival time offsets is. This all has to be 32-bit aligned, so if the gap between begin and end sequence number isn't a multiple of 2 packets, it'll need to be padded. So there's a little bit of detail to be done there. Other than that, it's essentially the most straightforward possible encoding of this information. Next slide, please. We've defined this as an XR block. It's fairly clear to see that if we define this as a custom RTCP packet type rather than an XR block type, you could encode the same information losing 4 octets. And there's a little bit of overhead due to this being an XR block. And it might also be possible to optimize the format of the data. And I think it's fairly clear we could reduce the size of that data. And to do so would save bandwidth at the expense of perhaps a little bit of extra complexity. I think it's important to note that since we're sending this as a compound packet, compound packets must contain a sender report or a receiver report and a CNAME. Accordingly, the minimum overhead of all of that is 80 octets. So you have a minimum 80 bytes of sender report, receiver report, and an SDES CNAME item before you have the feedback. And if there are multiple streams here, then there will be higher overheads. Accordingly, my personal belief is that it's not particularly worth optimizing the XR block format, given that you've got at least 80 bytes overhead on top of it anyway. Next slide, please. Okay, the other approach to doing this was to use non-compound packets, which can be sent as part of the AVPF transport layer feedback. This is a way of reducing the overheads, since the non-compound packets, when they're sent, don't have to include the sender reports, they don't have to include the various report blocks. However, you do still, if assuming I've read all the various specs correctly, you do still need to send scheduled compound RTCP packets as well. So I think the way you have to do this is send your regular RTCP packets and then fill in the gaps with non-compound packets in between. Next slide. The non-compound packet format, the format looks essentially the same as the XR block format. The only difference is that we're putting the timestamp at the end to match the standard format of the transport layer feedback packets. We can probably align the XR block format to have exactly the same contents, although this version of the draft doesn't do that. But it's exactly the same information, formatted slightly differently, but sends us a non-compound packet without the sender report and without the SDES. Okay, so after echoing too much, it's now gotten quiet. Okay, all right, next slide, please. So what's in this draft? It's a simple way of encoding the required information, either as an XR block, which can be sent as part of a scheduled compound packet, or as a transport layer feedback packet that can be sent in a non-compound packet between the scheduled reports. The format has not been optimized in any way. We can clearly optimize it. I know Michael has a proposal to do that. I know Varun has been making suggestions on that way as well. To me, it's unclear that this is worthwhile. There are likely to be very few reports in these packets, and even if we end up saving a factor of 2 on the reports, we're still probably only saving 8 bytes per packet, and at least in the XR case, there's an 80 byte minimum overhead, so I think that doesn't make any difference. We can use non-compound packets. That gives a pretty big, that gives a massive saving, and my personal opinion is that that's enough saving to get reasonable savings, but I know there are proposals to save that, and we could do that if the group thinks that's an appropriate thing to do. The questions for the working group, is this the right information to report? And I think the design team is all in agreement that this is the right information. Is the way we're encoding it in either XR packets or transport layer feedback appropriate, or should some of the proposals for optimizations, which you're going to hear about in a minute, be adopted, and is it reasonable? Should we be optimizing this? So, I don't know if we wish to discuss them now, or if we want to hear Michael's presentation about some potential optimizations first, and then after Michael, I have a presentation on the RTCP overheads. So I don't know how you want to do questions.
So let's see if we have any short questions and clarifications, but we leave the longer discussion to after. And I see we have Randall in the queue, so we'll take that question.
Yeah, just a short clarification. Not only is there the 80 bytes of overhead for the compound RTCP, in both both XR and RTCFB things, you also have IP UDP overhead of, I remember correctly, 828 bytes per packet. And also, if it's encrypted, which typically it would be, and certainly will be in WebRTC, another 10 bytes of authentication tag. So the overheads add up.
Yep. Yes, I agree, and I certainly included the UDP headers in the analysis that I'll be presenting later, although I don't think I included the encryption overheads.
Okay, any other short questions or questions of clarification? Otherwise, we move and let Michael present the optimizations, and then we can have a bit more discussion at the end when we've seen all three related presentations.
Sorry. I think there's a comment meant for the room from Varun Singh. This is Jake Holland, JavaScribe. That this feedback does not just apply to per packet frame feedback, however, can be sent in longer feedback intervals. So,
yeah, so the question, if I heard it right, was that it doesn't justify per packet feedback, but can be sent in longer intervals. Yeah. I mean, the draft I'll be presenting in a few minutes does talk about that and talks about how often you can get feedback. So yes, I agree, but we should probably defer that discussion until after the later presentation.
Great, thanks.
Okay, Michael, you're on.
Very good. Thank you, Anna, and good afternoon, everyone. I'm seeing the last slide on my screen. Can I slide? First one would be great. Okay, so thanks again. This is a readout of a proposal for the feedback. It's an intermediate output. That is, it didn't make it into the draft yet. The design team that kind of worked on various aspects of this, and by the way, this is a work in progress. This is not done. Whose names are mentioned there in no particular order. The asterisk means that not everybody agrees to all the things I'm probably going to say here. So with that, we'll just go on to the next slide, please. So to address this, what we have is we start out with the message format that Colin presented a while ago, and then talk a little bit about what we did at design team to say how we might want to modify or change this based on some of the calculations that actually Colin will be presenting in the next presentation. And then a proposal for a new format, but more importantly, a socialization of ideas. This intermediate proposal did not end up in a draft, and therefore it's kind of like half-baked. Next slide, please. So for completeness, this is the format that Colin just presented, and I just want to focus in on a couple areas. He talked about the report timestamp, and he talked about the generalized format, but the 3 bits that we really want to focus in on this report is for every packet reported on, there's this 16-bit quantity, of which 3 bits are taken up in front of something called an arrival time offset, which is a time relative to the report timestamp that actually says indicates when the packet was received. The 3 bits are, one is an L bit, which is simply a loss indicator. So right now that indication for loss is in every single one of these 16 bit blocks. And then the 2 ECN bits that we want reported because we may want to know their values. So we notice that this is all these 3 bits are taking away from some of the range of the times that we could report in arrival timestamps, and we are asking ourselves, can we do better given a couple things? One is that we know how to efficiently encode loss information in the form of a bit vector via run length encoding, and the other is that not everybody would necessarily be the ECNs on all the individual packets because oftentimes they're all the same. So there was a desire in the group to investigate some of these options for compressing all of the fields in every one of these 60-bit blocks. Next slide, please. So we had a meeting on September 28th, and it's been mostly quiet on the list up until very recently. So we encourage people to add their 2 cents here to give us additional guidance. But the goal was, before Colin got done with the work that you'll be seeing just in a little bit when he presents all the calculations, was there a different design that was more amenable to trivial or easy compression if we in fact knew that we needed that? So some of the results that Colin actually previewed here is that perhaps this is diminishing returns and we don't need to do this, but the design team back in September decided, why don't we look at this? Is there a better way to structure it to give us other operational advantages and the potential ease to compress the format if we wanted to in the future? And there also seemed to be the desire, as I mentioned before, to separate out the ECN components into its own field for the cases of when they're identical and to trivially compress them. We also talked a little bit about perhaps we would signal about whether or not we wanted the ECN bits. That thread has gone quiet. But more importantly, is particularly for some of the measurements we've done over wireless, we would like to actually have as much dynamic range in those arrival time offset fields, independent of what the timestamp is. We decided in the working group tentatively that a good granularity was 0.1 milliseconds, 100 microseconds, but that would be a default, that you could actually signal an intention to use a timestamp granularity different than that. So next slide, please. So this is the proposal. It is an intermediate work in progress. And in fact, I'll mention something that, or a few things that perhaps people from the floor will want to address. Like the previous proposal, has the same header information and also gets reported per SSRC. But one of the things that we did here was to maximize actually the dynamic range of the arrival time offsets. So every one of those 16-bit quantities now is dedicated for almost to the 16th unsigned integer granularity for the timestamp, and we've decided to move the ECN bits and also the loss bits elsewhere. And that's the part of the proposal that we'll be debating a little bit. So to do that, one of the things that I proposed, and it certainly can be revised with other ways to do this, was to steal a couple bits from the end sequence number. Because unlike a normal XR block that probably could report on a vast number of packets, the intention here is that the feedback would be as frequent as possible, often subject to the constraints of RTCP feedback. But in no case do we expect a really, really large difference between the end sequence and begin sequence. So I stole 3 bits from the end sequence field and encoded it as a delta field. So you simply do a modulo to sum of the delta and the begin, modulo to the 16th sum of the begin sequence and end sequence, and you end up inferring what the end sequence is, and use those 3 bits to signal the following: that if the E bit was set to 1, it kind of meant that all the ECN bits were the same, and you just simply report them in the next 2 bits, which I've labeled ECN. If the ECN bits weren't all of the received packets weren't all the same, we had two options. One is that maybe we don't want to report them if your signal is not important, or you could actually report them individually in a block that comes after all the ATOs, the arrival time offsets for all the packets that were within the range of begin sequence and end sequence. So that is shown on this diagram as a series of K2 bits labeled C11, C12 as being the ECN for the first one, and then all the bits after that. In both cases of the ATO and the ECN bits in the C blocks, you need potential zero padding to align them to a 32-bit boundary. So absent there, you see that there's no loss bit. So what I proposed was that we used one of the code points for the ATO to actually indicate that there was a loss. So if you had all ones, it just meant that that packet was not received. Therefore, there's no time associated with it. Therefore, any ECN bits that you also would associate with that missing packet are not relevant and not meaningful. And then also modified a little bit to say that if you had a value of FFFE, that just simply meant that the offset was larger than that which could be represented in the field. So this is one of the intermediate outputs. It wasn't a design team consensus, so to speak, never ended up in the document, but we did want to socialize it and also mention two other things. One is an idea from Varun, which he may comment on soon hereafter, is that we've got an efficient form already to take a bit loss vector and run length encoded. It's already defined in our TCP/XR block type, and we could use the same mechanism there. Put it someplace in here to actually identify whether or not a given packet was received, and then we wouldn't have to send any data in any ATO block of 60 bits to identify it. The other thing that I mentioned previously is that if the ECN bits are different, we've got two ways that we could actually efficiently encode those. One is a run length encoding on the 4 symbols instead of the bitwise decision, or we could bitwise run length encode those. But now we're getting to an uncompressed format that actually has one or two elements of compression in it. The good thing is that the thing that's left over, the 16-bit ATO blocks, are themselves very easily compressible by a range compression or a form of difference in entropy encoding. So what we're struck with is that if we go to using the loss vector compression, we end up with an uncompressed format that already has an element of compression in it. With just a little bit more effort, we could compress the ECN bits, and perhaps with a little bit more effort there, we could compress at decent compression the remaining fields. So we're in between this space where Colin's presentation in the next slot will assume that none of this is compressed, and he'll come up with some figures, and we'll have to figure out how significant to work to compress this is relative to the benefit that's possible. So that's where we are right now. And I'd like to admit a couple other questions from the floor if that seems like the appropriate place between now and Colin's presentation, or after Colin's presentation, your call. I see Mo's there.
Mose and Addy had a suggestion maybe to also consider looking at what the flexible FEC payload format does for this. It's marking, it's trying to mark, a range of packets for protection, not for loss, but you could look at that and similar structures in 5109, the unequal error FEC protection. There's just the beginning sequence number and then a mask, the mask of which other bits, which other packets to apply. You could do the same thing here. You could have the beginning sequence number and have the mask instead of the end sequence number. And that mask would tell you which ones you're actually reporting on, which ones were received and are going to have, time offset data. And then all the lost ones you don't care about, so there's nothing to report on. So maybe take a look at that payload format and see if it's another idea that you could use.
Yeah, we should do that, and Varun and I will think about that. That's in a very real sense, Varun's proposal to use the run loss encoding in the XR blocks is effectively defining a mask. So yes, thanks, Mo.
Right. Yeah, the first one from Jabber is Varun, so why don't you go ahead?
Okay, Varun, you should be on.
Okay, I didn't see myself. All right, so I had two comments. One was the fact that it was mentioned before that it's 10 hours. That you have, there are two things I want to mention. One is that there is burst losses, which means that there are situations where at least 5 or 10 packets get lost altogether at once, in which case what I have today just shows a series of 0xFF, which is not really useful because you could just encode that in one bit. And the second bit was that in video sequences which are above 500 kilobits per second, the number of packets in a frame are typically above 20 and up to 50. So if you're talking about frame reports, or unless you're talking about packet reports, a frame report would actually have 50 packets in it. So a burst loss would tend to have a lot of bits encoded as ones. So my proposal, I think that's already sent to the list, was to use an RLE similar to what Mo just mentioned 2 seconds ago, was to encode the RLE at the top so that you can skip the corresponding ATO bits. Especially in the case of burst losses, it would save significantly at high bit rates.
Yeah, I agree with that statement, particularly on wireless links. And that's yet another reason why we like to have the ATO field as large as possible. I've personally measured over LTE, although I wasn't very nice to the LTE. I was kind of bashing it, delays and then burst losses, delays of over 2 seconds and then sustained burst losses. So both compressing the format for those sorts of applications, those kinds of situations, it's probably worthwhile. Thanks, Vern.
All right. Jake Holland, JavaScribe for Gory Fairhurst. Michael, I may have missed this, but I wanted to check if this method could potentially hide the presence of a CE mark, specifically receiving a CE marked packet and not reporting. Seems like something we may wish to worry about.
To the extent that the CE mark is in the ECM bits, we should be able to report on those.
Okay. We have Randall in the queue.
One quick note. Varun indicated a frame at 500K BPS or higher be 20 to 50 packets. That seems way high on number of packets. You could, if you're filling the packets reasonably well, like over a K per packet, 500K should be 2, maybe 3 packets per frame, or somewhere on that order. 20 to 50 packets sounds more like 5 megabits or something much, much higher. So still, I mean, it is an issue of how frequently you're reporting as well. But if you're talking about per frame, it's going to be much lower.
Yeah, so that's the end of my presentation. Anna, I would encourage folks in the audience who want to participate on the design team to just let us know. I was also negligent at the beginning. I was going to give Zahid a shout out. He's been the herder of cats to get us all together to actually have these meetings. And it's very much appreciated and sometimes a thankless task. So thanks, Zahid. Thanks.
All right. One more question from Xiao King. I have the same question as Randall. The traces I just presented has about 5 KB per frame at 1 megabit per second.
Jonathan, so my question, so I assume from the fact that you have the offset bigger than FFFD, the offsets are relative to the, they're not differential.
That's correct. The report timestamp is an anchor. And this is the same as the proposal that was in the 01 draft, that it's an anchor upon which all the arrival time offsets are relative to that time, and we're very careful in the draft to say that that's an anchor time, that report timestamp is not necessarily as good of a timestamp as you can get for the time at which it was sent out. It will, of course, be close, but we're doing processing, and we're getting this timestamp, we're doing all this arrival time offsets relative to it. We may be doing compression, OS burps occur. So yes, all those ATOs are relative to the timestamp in there. And the reason why we actually like the overflow part, Jonathan, is that if the sequence numbers in some of these reports overlap, perhaps in the newest one, you find out that the offsets are in one of those reports, you'll be able to get a very accurate time, and maybe the other one will have happened so far in the past. In a particular case, maybe your implementation just says X packets, and there was a pause or some sort of mute in there. Some of them may be very much older, but you may already have that information in the previous feedback packet. So that overload says that the packet was really long relative to the report timestamp. We don't know it unless you got information on the timestamp from a previous feedback report, which can keep it, right? So you already have it. So those are the two utilities for the kind of overflow code point in that ATO offset.
The other question I had, and maybe this is more a general design team thing, is I feel like there's times when you would like to be able to say, because of an OS burp or whatever, this packet was received, but I don't have good information as to when it was. If you try to, if you try to act on when I thought it, when, the second and a half of my OS being scheduled out, you're going to have very bad results, so better just to ignore this. Is there any way to say that?
I think that code point effectively does that for those packets that you haven't gotten already via a previous feedback packet accurate information on. So you could actually put some words in the document, they're not there now, that says this is for the case where we can't represent it in that 16 bits. If you've got better information from a previous packet, please use that. Or for some reason we've decided that this packet timestamp is wrong, and to ignore it. So we could actually put that in the document. That's a good point. I'm going to write that down.
Mosinati, in those graphs that Xiaoxing showed, those big spikes at transition times were iframes, and I thought that's what Baron was talking about. Having large numbers of packets per frame. You're going to easily get much bigger than 2 to 5 packets. You're going to be getting on the order of 20 to 50 packets for those iframes, and unfortunately, that's when the congestion is happening. That's the reaction to congestion. So we want to make sure the format works good during actual congestion. If we optimize it for the 2 to 5 packets per frame case, when there's no congestion and it's good, that doesn't really help us much. We really need to make sure that we're optimizing for the times during congestion when we know we're going to have transitions and in resolutions that cause these iframe spikes. So let's make sure it's a very good format for a 20 to 50 packet iframe, because that's what's going to happen during congestion.
Ruins RLE is looking better all the time. Okay.
Hi, Colin Perkins from the FlowMake. Two observations. The first is that if we are compressing this, then the loss patterns clearly matter. So we clearly need to think about what patterns of isolated versus burst loss we're likely to see, and use that to evaluate. Because that will affect the size of the packets, because it will affect how well they compress. The second observation is that since the reports are sent regularly, there is a maximum time between RTCP reports. so we can bound the maximum offset needed. So we don't necessarily need ultra large offsets because there's a bound on that, even if the packets are arbitrarily delayed.
A slight pushback on that, Colin. In general, I agree with that. The LTE cases that I mentioned when I really pounded the link and had these 2-second delays, primarily because the schedule said I was a bad buy and it was going to hold up my packets. So even if you had the reports every X number of milliseconds, right? If the scheduler decides to hold me up for 2 seconds, it doesn't matter that you scheduled them. I'm still not going to get them. So there is some utility in having the ATO field kind of as large as reasonable. And right now, I don't know what that number is, but I do know that greater than 2 seconds is probably, we see that in the Sprout work too, that you've had over 2-second delays. Right now, the ATO field can handle 6-point-something seconds, and that's I think well beyond, or at least a factor of 2, if not more, larger than our ever anticipated need for real-time service.
Again, Colin Perkins from the Flow Mic. I'm perhaps misunderstanding you, but it doesn't matter how long you're blocked, how long the packets are delayed for, because you still report every half second, or whatever.
Yes, and
there is an upper bound.
Yes, I was assuming though that, and by the way, this part was not discussed much on the design team, with that there could be overlap in the reports, and that it would be useful for the rate control in the case of one being lost, right? That you had some information on some older packets. So depends on how old the older packets are. I think I'm done. I didn't hear anything.
Yeah.
Okay, Charging.
Yes, thank you. Yeah, so I guess I wanted to respond to what Mo has said. Thanks for the clarification. At least we got the mask straightened out that way. So we understand that the 20 to 50 packet is for the iframes, but I don't see why that burst of frames need to be sent out back to back within a frame interval. Is that intended? Because that doesn't seem to be the right thing to do. Because potentially for instance, the RMCAT congestion control solution also has the possibility of imposing a transmission queue to smooth out the transmissions, because it doesn't make sense to impose self-introduced congestion. So that even if you can get a spike of, so basically, even if you can get a spike of 20 to 50 packets per frame, it doesn't mean that you would see that within a very short window of a frame interval. Just wanted to raise that observation as well. Thank you.
All right, and Varun asked clarification on that point, I think. Does that mean that greater than 500 kbps, there are spikes of 20 to 50 packets? He also offers to share logs from callstats.io and says that the ATO is relative to report time.
Okay, thank you. And thanks, Michael. I think we move on to the next presentation. Colin.
Okay, hi, Colin Perkins again from the Flow Mic. So this is the draft on RTP congestion control feedback. The point of this is to do an analysis of what rates of feedback are possible using RTCP as specified, and figure out whether what's achievable is appropriate for the applications and the congestion control algorithms. Next slide. So the question to be asked is, can we send RTCP feedback using the existing mechanisms often enough to be useful for the applications, for the congestion controllers? The congestion control clearly requires reasonably fast feedback, either on packet loss or ECN marks, or of packet timings if we have got a delay-based algorithm. And as we say, we need to figure out whether using the mechanisms, and the analysis is currently done based on the 0.1 version of the design team draft, whether using those mechanisms we can get feedback sufficiently often that the congestion control works without having too high a RTCP overhead. We're assuming a modern RTCP implementation, so we're assuming we can run the AVPF profile or the SAVPF profile, although a lot of this does work if you just assume regular 3550. We're assuming non-compound packets can be sent. You've got RTCP-XR, you're using the 7022 format for CNAMEs, and if you're running multiple streams, you've got the aggregation fixes from the multi-stream draft, and you've got reporting groups from the multi-stream optimization draft. This essentially matches what a WebRTC implementation should be doing, although it's not representative of a lot of SIP implementations, but a WebRTC implementation should do this. Next slide. So I'm going to do an analysis for two scenarios. The first one is a simple voice over IP scenario. The second one is a video conferencing scenario. So if we assume, to start with, we're in a two-party voice over IP call. We have two participants sending. They generate each participant generates a frame of audio every what we call TF seconds, where TF will typically be 20 milliseconds, perhaps 40 or 60 milliseconds. And they're both sending continually, and they may switch to comfort noise or something, but they're both sending often enough that they count as active senders for the RTCP bandwidth calculation. And we want to send congestion control feedback every NR frames. Now that might be every single frame, it might be every 2, 3, 4, 6, whatever it is frames, right? And that's a configurable parameter. Since we're wanting to send feedback every NR frames, and each frame is TF seconds long, that means we need an RTCP reporting interval of TF times NR seconds. RTCP packets can be regular compound packets, or they can be non-compound packets sent using the early feedback. The analysis is done on the assumption that there are NNC non-compound packets sent between every compound packet. And if you set NNC equals 0, that's the case where you're only sending compound packets. And perhaps typical case might be NNC equals 1, which is where you send you use the AVPF to send a non-compound packet, a single non-compound packet between every compound packet. Next slide. So if we look at what's in these packets, the compound packets will comprise a RTCP sender report, a source description packet containing the CNAME item, and an extended report with the congestion control feedback in it. All of this will be sent in a UDP packet inside IP. For the purposes of illustration, we're assuming UDP with IP version 4, no IP options, which is 28 octets. A sender report is 28 octets of sender information plus a single report block, since there are two participants in it and each reports on the other participant, which is an extra 24 octets. There's a source description packet, which comprises 8 octets of header, 18 octets for the CNAME item using the 7022 format, and a couple of octets padding to map it out to a 32-bit boundary. And then there's the extended report packet, as in this particular analysis, as described in the 0.1 version of the design team draft. That comprises an 8-octet header, an SSRC, 8 bytes for the block types and timestamps, 8 bytes for the SSRC and sequence number range, and 2 bytes for each packet on which it's reporting. If we're reporting every NR frames, and each frame is a single packet, that's 2 NR packets. You add all that up, you get a packet size of 132 bytes plus twice NR. Okay, next slide. You can also send these as a non-compound packet. If you do that, you just have the UDP IP headers and then the feedback packet. You do the sums there, you find out that the packet is 48 bytes plus 2 NR. Slide. All this is sent, we're sending compound packets with some number of non-compound packets in between them before the next regularly scheduled compound packet, using the AVPF and the transport layer feedback and so on. The average RTCP packet size will therefore be the size of a compound packet plus the number of non-compound packets times the size of a non-compound packet, all divided by the sum of 1 plus the number of non-compound packets, basically averaging over the repeating pattern. And that gives you an average RTCP packet size. And you can plug in number of non-compound packets equals 0 if you want. Next slide. Okay, so that gives us the size of the packet. If we work through RFC 3550, the RTCP bandwidth calculation in there boils down to the reporting interval is the number of participants times the average size of the packet divided by the RTCP bandwidth fraction. In this particular case, there are 2 participants, so n is equal to 2. The average RTCP packet size is as on the previous slide, and the RTCP bandwidth is the amount of bandwidth that has been allocated to RTCP in octets per second. If we want to report on every NR frames, or each frame is TF seconds in duration, we want a reporting interval of NR times TF. We put these two together, do a little bit of algebra, and you come out with an expression for the required RTCP bandwidth in terms of the number of participants, the size of the packets, the number of non-compound packets, the number of the frame duration, and the number of frames after which you want to send feedback, which is given in this nasty expression at the bottom. And that says if you want to send feedback, every NR frames where the frame duration is TF and you have n participants and you're sending n sub nc non-compound packets in between them, you need that much RTCP bandwidth fraction to be able to do so. Okay, next slide. Now, what does that mean in practice? Well, the chart here on the left plugs in some numbers for that. It says if you set a particular framing interval and report every NR frames, what bandwidth do you need? So for example, if you set your packets to be 20 millisecond packets, so you're sending a speech packet once every 20 milliseconds, and you want to send an RTCP reception report for every second packet you receive, you need to set your RTCP bandwidth to be 53 kilobits per second. As you increase the number of frames before you report, the bandwidth goes down. So if you have a 20 millisecond packet and are reporting every four packets, you need 27 kilobits. And we work our way down to the end, where if you're sending 60 millisecond frames, 60 milliseconds of audio in each packet, you're reporting once every 16 packets, i.e. roughly once every second. You need your RTCP bandwidth to be 2.7 kilobits per second. This is making the assumption that you're only sending compound packets. There's no non-compound packets in here at all. This is just using regular compound RTCP packets. So provided you can set your bandwidth to somewhere between 2.7 and 53 kilobits, depending how often you're sending packets, how often you report, you get that much feedback. Now, clearly 53 kilobits per second of RTCP is quite a lot for audio. 2.7 is not so much. Next slide, please. Okay, if instead we alternate and we send a non-compound packet, so we alternate sending compound and then non-compound packets and then compound and then non-compound and so on, that reduces the bandwidth significantly. So in the case of 20 millisecond frames, report every second frame, this reduces the bandwidth to 36 kilobits. And in the low rate case, we're down to 2 kilobits. It makes much more of a difference reporting up very frequently than when you're reporting less frequently. And yeah, we reduce the overhead significantly because we're not sending sender reports, we're not sending source description packets. If you could send more than one non-compound packet between every compound packet, you would again reduce the overheads even further. It's not clear that's currently allowed by the reduced size RTCP RFC, although it would seem like a very simple extension. I don't know. It's possible it messes up the size calculations. I suspect it was just. I suspect what's happening is that AVPF is based on the assumption that you send one packet early. And then go back to the regular timing, and this is just reusing that mechanism. So I suspect it's just a consequence of that, and no one has done the analysis to check that it's okay. I can't, off the top of my head, think of a reason why it would break anything, as long as you send compound packets occasionally.
Yeah, John, thanks. I think if you're using TRR int, then you're essentially not sending compound packets on the slots where you're allocated ones. So you can, in theory, push your regular compounds up, to.
Yeah, I think you can push it out. I never quite understand TRR int, but I think I think it would be safe to push the compound packets out. So as long as you send them occasionally,
Yeah,
you
basically
send
out
several.
to roughly like AVP level feedbacks.
Yeah. I mean, you need to send them every so often, so you get the sender reports and you get the source descriptions
but,
and
if that's
stuff.
on the order of seconds, it's probably safe for most.
That would be my guess. Yeah. Okay, next one. Okay, so that's for the voice over IP scenario. The second scenario we looked at was a video conference. The assumption here is that you've got 2 participants in the session, each of which is sending audio and video. So in this case, you have 4 SSRCs, and we're assuming they're all bundled onto a single 5-tuple. So each party sends 1 SSRC representing the audio, 1 representing the video. We're assuming the video framing interval is TF, so the frame rate is 1/TF frames per second, and we want, again, a reporting interval of NR times TF seconds. That is, if NR equals 1, we're sending a report for every video frame. If it's 2, we're sending a report for every other video frame, and so on. And we can send the packets as either compound or reduced size non-compound packets. Next slide. Start by looking at the format of the compound packets. Now, since we have 2 SSRCs, what we want to do is aggregate the feedback from these 2 SSRCs into a single RTCP packet to reduce the UDP IP header overhead. So we send a single UDP packet, which has a compound packet from the audio SSRC and a compound packet from the video SSRC within it. We're assuming the reporting group extension in the RTP multi-stream optimization draft is used. That means one of the SSRCs is designated as the reporting SSRC, and the other one is the non-reporting SSRC. And the non-reporting SSRC delegates its sender reports and so on to the reporting source. So you only have to send 1 sender report. The reports are aggregated. It doesn't matter which one is chosen as the SSRC. You get the same effect whichever, as the reporting SSRC, you get the same effect whichever way around you put it.
Sorry, a comment from Ingemar Johansson that I think it was from a short while ago. I had the same understanding of TR in IE. One can use it to control the transmission of compound RTCP.
So you can send arbitrary numbers of non-compound packets between the compound packets. Yeah. Okay, cool. Okay, next slide. Okay, so if we look at the compound packets, to start with, the non-reporting SSRC. What will be in this packet is an empty SSRC, an empty sender report, so just the sender information block and no reports because they've been delegated to the other SSRC. A CNAME packet and the RGRS packet, which is the reporting group stuff. Next slide. In the packet from the reporting SSRC, you get a sender report with 2 report blocks, 1 for each of the SSRCs sending audio and video from the other participant. You get the CNAME packet, and you get an RGroup packet, which is the other part of the reporting group's extension. And you have the XR block containing the reception quality feedback. The sizes of those, the sender report will be 76 bytes, the source description packet will be 48 bytes. The reception feedback packet will be 8 bytes for an XR header, 8 bytes for the congestion control report header, and then for each of the SSRCs, you've got an 8-byte header and twice the number of packets being reported. That gives it a size of 32 bytes plus twice the number of audio packets being reported plus twice the number of video packets reported, because there's 2 bytes for each audio and 2 for each video packet. That means the packets from the reporting SSRC are 156 bytes when you add all of this up, plus twice the number of audio packets reported on, plus twice the number of video packets. Next slide. Okay, so you put all this together. You've got your UDP IP headers, you've got your packet from the reporting SSRC, you've got the packet from the non-reporting SSRC, all of which are aggregated into the same packet for transmission. That gives you a total of 252 bytes, plus twice the number of audio reports, plus twice the number of video reports. Since it's aggregated and reporting on 2 SSRCs, you halved it before use, which gives half of that as the size of the compound packets. Okay, next slide. So what does the RTCP calculation look like? Well, we're assuming essentially constant rate media. Now that may well be the case that you're sending an iframe and the iframe is big, so you then don't send the following p frames for a little while to allow the iframe to be clocked out. But we're assuming things are roughly equal, roughly constant rate. We're assuming the video frames are of roughly the same size, audio at 50 packets per second, and an MTU of around 1500 bytes. The assumption is we just split the, we take the, okay, we're sending at 1 megabit per second, and we're sending 1500 byte packets, and you just divide one by the other to get the number of packets per frame. The bandwidth calculation is the same as in scenario 1. I'm not going to talk through that, the nasty expression. It's the same one we had earlier. You plug in the size of the compound packets from the previous slide. We'll assume no non-compound packets for now. TF based on the chosen video frame rate, and we're assuming we're reporting on every single frame of video. Next slide. Okay, so if you do all the sums, plug in some numbers. The leftmost column is the media rate, going from 100 kilobits per second down to 4 megabits per second. You do the calculations, you divide that frame rate up by 1500 byte packets or thereabouts, and you get about 8 packets per frame. No, you get about, sorry, we're looking at 8 frames per second for the 100 kilobit case, going up to 60 frames a second in the 4 megabit case. You divide that up, you get the number of video packets per frame and the number of audio packets per report, assuming audio being sent 20 millisecond packets. And the number of video packets per report ranges from one per frame up to 12 per frame for the 30 frame per second 4 megabit case. And the number of audio packets goes down. It's just based on the frame rate and a 20 millisecond audio packetization interval. What we're seeing on the rightmost column is the required RTCP bandwidth in kilobits per second, and then in brackets after that, what fraction of the media rate that is. And again, we're only sending compound RTCP packets. There's no attempt to use non-compound packets, and we're reporting for every frame. And if you change how often you report, if you report every second frame, for example, you can halve all of these numbers. Every third frame, you reduce them by a factor of 3, and so on. What we see is the required RTCP bandwidth for the 100 kilobit case is about 33 kilobits, about a third of the session bandwidth, which is clearly too high. And in the cases with the very high rate sessions, we're down to sort of 5-6% or thereabouts, much lower overheads. Next slide. Okay, what about the reduced size packets? What would be non-compound packets, except they can't be non-compound because they're aggregated into a compound packet. What we're sending here, if you work through it, you can omit the sender reports and the CNAMEs because these are sent as reduced size packets. So you just get the source description, reporting group, the RGRS packets, and the XR feedback packet. And this should probably be probably be the transport layer feedback instead.
Jonathan, I'd argue you probably don't need the RGRS.
You possibly don't need it, but I think the spec says you require it.
Really?
I think so, yes, unless I've misread it.
We should have fixed it. That's wrong.
So yeah, it's still in the RC editor queue, so we can fix it if need be. Yeah. You work through these sums, it gives you this size of 96 bytes plus twice the audio and twice the video, and again halved because it's aggregating 2 packets. Okay. All right, so we repeat that calculation again. This time we're assuming that we're alternating regular and reduced size packets. Next slide. Okay, so it's the same calculation as before. We see the overheads have gone down to 25% in the 100 kilobit case and to 4% for the very high rate cases. And again, this is reporting on every frame of video. So if you report every second frame, you can have all of these numbers. And I haven't done the calculations, but you can plug in the numbers for two reduced size packets between every compound packet, or 3 or 4 or whatever. Next slide. So to summarize, that's a lot of information. The draft does try to walk through it. It's entirely possible I've made a mistake in the calculations. There's a lot of calculations here, and there's a lot of RFCs to read. So please do check it and make sure I haven't messed this up. It seems that depending how you configure things, you can get either very high or relatively low overheads. My impression is that if you take care with the way you configure your RTCP and how often you report and make judicious use of non-compound packets, then you can get pretty reasonable overheads for all the cases we consider. However, you do need to scale the feedback with the media rates. So as your media rate goes down, you need to send less feedback. Alternatively, you could say as your media rate goes up, you need to send feedback more often, which seems a perfectly reasonable thing to do. If you're sending faster, you should send more feedback to control that. I think the questions for the group are, can the congestion control candidates operate within the amount of feedback that's being proposed with reasonable overheads? Are these overheads and configurations things which are acceptable? And do we need, what guidance, if any, do we need to give implementers for how to configure our TCP? And as I say, we've talked about non-compound packets. We could rerun this with more non-compound packets, and that would reduce the overheads a little. And equally, we could optimize the formats a little, which would also reduce things perhaps slightly.
Jonathan Knight, so my question here is, you say they need to report on a smaller fraction of media frames. Do you mean send feedback? I mean, you're still reporting on all the packets, right? You're just sending feedback every n frames rather than every frame.
Yeah, that's what I mean, right?
Okay.
So it's like the audio case where instead of sending every 2 frames, you're sending every 16 frames, but it always reports on all 16.
Okay. All right.
It reduces the header overheads, so the overhead gets amortized over the duration.
Okay, we have Randall in the virtual queue.
I can't hear you,
Sorry,
Randall.
we can't hear you yet.
Sorry, hardware mute got me. Thanks for all the calculations, Colin. That's very useful and very helpful. A couple of things to note. One we mentioned already, which is that none of these assume an authentication tag for encryption, which would add typically 10 bytes for every packet. So that'll adjust those numbers somewhat in an obvious way. The other thing to note, I would note, and Colin just mentioned it a second ago, is that I don't see much reason to send compound ones frequently, unless there's some other reason to send an SR or an RR. I would send all non-compound, and that will reduce things somewhat.
You do need to send SDS packets occasionally, so you do need to send compound packets occasionally, but that could be at the sort of 5-second interval.
Yeah, exactly.
Like regular AVP.
Yeah, those things you need to send at the same rate you would need to send them normally if you weren't doing congestion feedback here. Okay, and that, like you said, on the order of seconds. The other thing is that this is obviously very strongly driven by the overheads involved, even in the non-compound version. Per packet overhead is relatively low. If you run out the reporting intervals to much longer intervals, then those become a significant fraction. However, my concern is that one of the driving factors here is that these are for congestion control, and typically the congestion control algorithms, in order to remain stable, need feedback reasonably often. This may vary according to the algorithm, but we're probably talking on the order of hundreds of 100 or a couple hundred milliseconds, not second times.
I mean, we're giving feedback. I mean, I think we need to give feedback on the order of a small number of frames. I think talking in terms of a fixed number of milliseconds isn't useful because you can only adapt per frame. So it's a fixed number of video frames.
I realize. Well, yeah, or audio frames. You can only adapt when you send data, obviously.
Yeah, but it's framing intervals rather than RTTs or fixed time periods.
And also note that on the video, even though officially it's like, oh, it's a frame, there's a big burst of traffic, really these are going to get paced out onto the wire anyways. So it's more of a especially for video, it's almost a continuous stream of packets. So
yeah, I mean that's the assumption that the video is essentially constant rate as a result of that.
Right. So the net result of this is, because of all those because of the overhead being a highly driving factor, especially when you report frequently, the percentage of the immediate traffic at low, percentage of the traffic that's congestion control at low bit rates is very high. In some of your cases, like 20, 30, 50%. For audio only, though you didn't give numbers for it, the numbers may be well over 50%, perhaps over 100% in some of the cases.
Well, I mean, they're not over 50% or 100%. They're 33% in the worst case, and I really don't think it makes sense to send an RTCP packet for every second audio packet received at that low rate.
Yeah, well, perhaps not, and that may be, and that's some of the cases. But if you're running a relatively low rate audio, say 20 kilobit per second audio, you're going to have a pretty high percentage. So but
you're not, because to get that low rate audio, you need to configure sort of 60 millisecond frames and
well, you don't, but that's okay.
You can easily configure your RTCP bandwidth down to 2% overhead, and we saw that in the earlier slides. And yes, you're reporting once per second, but if you only have 20 kilobits per second audio, you ain't going to do any damage if you're sending 20 kilobits per second for an extra second.
Yeah. So, but in any case, it's very useful information, and I think this highlights how much the overhead is the driving factor here. Thanks.
So we're starting to run a bit late, so please be brief at the mic.
I will be brief. Jörg, I think in terms of the guidance you want to give to the implementers, I guess, having looked at a number of these bits ourselves, the most interesting bit is at which intervals do you reconfigure your rate assumptions when you are building things based on a dynamically congestion controlled bit rate. And I think there's many different ways to get this wrong, to have weird ideas about this, to suddenly overshoot in term or undershoot. So that probably deserves some more thinking, going through and studying. And so if there's one thing that would be on my wish list, that would be it.
Okay. If you have any suggestions, please do pass them on.
Yeah, I mean, that would be really good if you have a suggestion. Perhaps it's not directly related to this presentation, but I think this is somehow related. So there was, we presented this one in FETX, and there was a discussion about XR block or feedback message. But I think that boils down to the question, like whether, I mean, looking at the overhead when you're sending compound packets, and when you're sending compound packets plus non-compound packets, what is the feeling here? Like, shall we be only targeting a VPF profile, or should we do the packet formatting both that's suitable for AVP and a VPF profile?
So even if we only target AVPF, you still need to send compound packets occasionally. So I agree we should align the format so it's the same blob of data being in an XR block or a feedback packet, but we do still need to send compound packets occasionally. Yes, and I agree that those are very much the biggest source of overhead. If you increase the number of non-compound packets between each one, the overheads go down dramatically. But yes, we do still need to include both. Whether it's an XR block or a different or a custom RTCP packet type, we could do that, and we'd save 4 bytes if we did. Yeah.
Okay.
Jake Holland on behalf of Bernard Arboba from the Java Room. The other thing to consider here is that loss and delay are not the only thing needed for audio. Opus has FECs, so info and burst loss is critical for adaptation.
Yes, I mean, and that depends on what information is in the feedback packet. So certainly the format which I did this analysis on includes complete, for every packet a bit to indicate whether it's received or lost. Yeah, I mean, obviously, if we're doing some RLE formats, that would affect the overheads, and sure.
Okay, thank you, Colin, for the discussion, and please continue on the mailing list, and I'm sure the design team is also happy to get further input. So we have one last presentation, so on the NS3 module. So while Colin is bringing the slides up, can I just ask where we have our blue sheets? One is there, but we're missing one, right? Anyone see the second blue sheet? Okay, great. And then Xiaojing is on again.
Yes, thank you. Yeah, this will be a relatively short presentation, and it's actually more of a preview than actually disclosure of information. And it's just to give a status update to report on a standalone modular of the RMCAT solution framework that me and my colleagues, Sergio and Jen Fu from Cisco, have been working on. This is basically a modular that can be added to NS3, and we're in the middle of developing it and also jumping through the hoops of getting it approved for open sourcing. Next page. But I'll share a little bit of the motivation and the general structure of it. So the idea for us to take on this work is really to come up with really to follow the spirit of running code or half running code in IETF along with the drafts. Basically, we wanted to test out a reference implementation of the RMCAT solution framework as described in the draft. And we wanted to be a standalone extendable code modular in NS3 so that it can provide as a base layer of service some common service for generating and/or generating feedback messages from the receiver side, and then also parsing and analyzing, generating delay loss and delay loss statistics on the sender side based on those feedback messages. So that would obviously reflect whatever is being designed by the design team for the feedback messages. And then on top of that, we want this framework to be able to accommodate different congestion controllers. So potentially, people can use this as a tool for comparing variants of their own, variants of congestion control solutions and drive their own conclusions, drive their own performance evaluations too. And finally, we wanted to support basically to be able to, we can plug in different traffic sources to it. So again, this is to provide the option of expanding the variabilities in our test scenarios. So for instance, we have enabled this code this modular to work with the sync codecs modular as a sub-modular in that NS3, just so that we basically allow sort of provide a platform for carrying out performance evaluations under a reference design. Next page, please. So currently, we have made some progress on this NS3 code modular. We have kind of completed the implementation of the baseline service, as I mentioned, as a baseline, as a base class of a sender-based controller, which is in charge of generation of feedback messages. We currently have our own kind of naive way of generating per packet feedback message. We're waiting on the input from the feedback message draft to update it and conform it to whatever the design team recommends. But the idea is really for the receiver to be able to report back per packet information on arrival time, loss, ECM marking, and also the packet size. So with that, the sender will be able to derive informations of delay, round trip times, packet loss ratio, as well as receiving rate based on these messages. And these are all being implemented as a base class of the sender-based controller so that all other congestion control algorithms will be able to leverage those common services without having to implement them again by themselves. Now, and also we have tried out 2 congestion control modulars. The first step was a dummy fixed rate controller just to make sure that all the APIs work. And secondly, as I mentioned in the earlier presentation, we have also implemented the NADA controller as a reference implementation of the draft. Our experience in going through that exercise really made us appreciate kind of the, some of the groundwork we did, because this is almost my 3rd time implementing the NADA draft. And this time, because I basically the structure of the code allowed me to follow almost sort of literally just simply implementing mostly the equations specified in the draft, while leaving some of the other, sort of mundane work of calculating per packet statistics, etc. Basically, I have been able to leveraging those services from the baseline sender-based controller. So that was some of the experiences in leveraging this framework. And finally, as I mentioned earlier, the code modular also accommodates traffic sources. By default would be CBR traffic, and also that shows up as called perfect codec as one of the idealized codecs in the sync codecs, and it's relatively easy to invoke other types of traffic sources too. We're still in the process of testing those out, so but the code structure already allows that. And finally, accommodating evaluation test cases, we have implemented both the eval test and the wireless tests, just the Wi-Fi section, since we previously had those code in NS3 in our previous version of the implementation. We're in the process of porting over those codes to this new NS3. And this new code modular more or less follows the coding convention and also the sort of structure convention of NS3 modulars. Just basically, the idea is that we want to be able to contribute this out open source as an additional modular in NS3 for people to test it out more freely. Next page, please. So as I mentioned earlier, this is ongoing effort. Therefore, we're still in the process of open sourcing the code and following a similar legal, sort of jumping through the legal hoops internally, as previously we've done those for the sync codecs codec, and if sync codecs, the code repo. And if you guys remember, it took us definitely longer, quite some time to going through that. That's why, unfortunately, I'm not able to talk in details about the code in a more concrete manner. And also, we're in the process of migrating all evaluations of NADA to this new code base. In the meanwhile, we're definitely welcome suggestions and contributions, but probably more practically, you guys will be able to give us more input after we're able to open source this, hopefully in a couple of weeks, if not longer. This is really more a preview of what we've been doing. And the main thing is that the idea of this code modular is to reflect the framework document that Zahi helped to present in the previous IETF meeting. We've relatively collected not many feedback on that yet. So on the draft itself, we also welcome people to provide us feedback on the draft. Thank you.
Hi, Colin Perkins from the floor mic.
Yes.
I just wanted, having played with NS3, I just wanted to thank you for doing this, because I realize this is a reasonable amount of work to port this code over.
Okay, thank you.
Jahid, yeah, this is same. I mean, same here. I mean, I played around in NS3 code, and I know how hard it is. And thanks for doing that. And we can also, you and me and everybody else who else have contributed to this framework document, they can thank themselves because they did a good job. I see, like you're saying, like that framework worked. But this is really good, and thanks for the good work.
Thank you.
Okay, thank you, Xiaojing, and please provide comments on the framework documents and further input. So we are out of time. and also at the end of the agenda. So this closes the meeting. So thank you all for coming, and please continue the discussion on the mailing list.
Okay, thank you guys.
Brings it much quicker.